installment of the 4C webinar series. Our host today is Gilad Shpitzer with Atmosfir, and he will be discussing D-fenceline measurement systems. And with that, take it away, Gilad.
Thank you, Steve. And I'm honored to give a webinar again in 4C conferences. I'm new to this conference. Actually, the first time I've attended was last year, and I really thank you for letting me speak again. A little background about myself. My name is Gilad Shpitzer. I'm born and raised in Israel, Jerusalem. I'm in the field of air measurement more than 25 years. Just a second. I started up as a source testing, and I also actually own the biggest source testing group in Israel called AS Research Services for source testing and in ambient air measurement, and we are ISO certified. And we also own Alchem. It's a chemical analytics laboratory conducting soil and air measurement, also ISO 17025. And we are in the final stages for ISO 17025 for Atmosfir D-fenceline System. So it means that what we're going to talk about today will be accredited worldwide in the next 3 to 6 months. So I will start with a few words about Atmosfir Optics. So Atmosfir Optics is a research development hardware software integration company that provides advanced air monitoring worldwide. We've got clients in Australia, through Israel, Canada, and United States. I am lucky because some of our scientists actually wrote the US EPA method, European and Israeli method. We did dozens of projects all over the world that we're going to see a few of them in this presentation and next week. And the company and the teams got several patents, including United States, Israel, and Europe. What is the D-fenceline system and what are Atmosfir Optics products and services? So we've got the D-fenceline system that uses open path instrument. It can use an FTIR that we're going to talk about mainly today, but it also can use a UV DOAS or tunable dyed laser. Tunable dyed laser is just for one gases. FTIR, it's for all the gases that got IR signature, and UV DOAS is something in between. It's good for the BTEX, but and mercury, but got disadvantages if you compare it to the FTIR. We also integrate point monitors like PID, FIDs. We combine with gas chromatography, MSA, H2S monitor, particulate monitor, and we can do a combination of both open path and point monitor. Our proprietary is actually the algorithm, or what we call the data checker software package, that help us characterization of the plume and improved quality assurance of any instrumentation. We also, beside fixed installation, give our clients a short-term project. We come with a trailer and we can do source location if you got a liquid that you don't know where it's coming from, or if you want to know what is the flux from your facility or from your combustion efficiency from your flare, or there is order that you don't recognize, for sure we can help you with that. So this is a few of our patents or our team patents, and they are in the field of system design. Actually, the design of the monostatic configuration is Robert design from the 90s. And we also wrote patents about improving the detection limit and data validity. That's what we're going to discuss today. And also source location and plume characterization. This is the last slide of sales pitch, and this is my last client told me that this is what convinced him, so I will say it. As a result of the quality of the D-fenceline system algorithm and software, Bruker, and if you don't know Bruker, Bruker is a $6.5 billion company that specializes in analytics instrumentation, chooses Atmosfir Optics to implement their solution for fenceline air monitoring. And with that, our client will have a reliable and robust instrument with worldwide support. They got offices all over the United States and all over the world. And together with our algorithm, we will give you a very good solution. So what are the objective of the D-fenceline system? We want to tell you when you got a leak, when it started, and for that we work 24/7, and we got a spatial resolution. We want to tell you what you emit. The system can identify simultaneously dozens of materials. One of my clients measured 50 compounds simultaneously with just one instrument in ppb level. We understand that knowing that you got a problem, sometimes it's even a greater problem that's why we want to tell you where is the source of the emission so you can go and fix it. And we all know that concentration, it's not all the time related to how much we emit, because also the wind played a factor. So we can give you, based on official method, the flux of the emission. So why we should use it? First of all, it will improve your environment impact. It will contribute to your health and safety. We can prove it's economic, cost effective. It will help you stay in compliance. You will find a problem before the regulator, or what we discussed before the satellite will go, or before the passive sorbent tube will find the leak. And it will improve your public relations. So what are our clients? So for sure, there are petrochemical industry and refineries, but also a lot of chemical plants, semiconductors, and government entities. So let's start a little bit about the background of air measurement. And this is a part of a presentation that I gave in 2017 in Washington to the Justice Department at the US EPA, and it was broadcast to all the regions in the United States. And the background goes like that. Most of the air monitoring methods were written in the 70s, 80s, with aim to control the emission from chimneys. And we succeed with that. We start monitoring the chimneys. The pollution goes out of the chimneys, went down. And actually, now the majority of the emission, we'll discuss where it's coming from, are not from the chimneys. Most of the air pollution, especially odor compounds and a lot of other compounds, we don't measure them routinely, for sure not in real time, and the environment. And we understand that a point monitor cannot represent and not characterization the emission from industrial complex. So if you want to design a measurement system, we want to know which air pollutants are emitted. So if it's just one compound or 10 compound, it will influence our system. The second question, we want to know what is the source of the emission. Is it tank farm or the flares or something like that? And when we know what we are looking from and where it's going out of, then we should decide where we should measure them. near, far away, downwind, upwind, a lot of other questions, what height, and then we should decide about the technique that we're going to use. So which air pollutants are emitted? 90% of the industry measure criteria pollutant, meaning particulate, NOxes, SOx, CO, etc. But actually, we don't measure amines, mercaptans, alcohols, sulfides like carbon disulfide, carbonyl sulfide, etc. Hazardous material like benzene, phosgene, acrolein, carbon tetrachloride, styrene, ethylene oxide that now is a big issue in Texas and in Chicago area. Acids. Actually, we don't have any official method how to measure them in ambient air. There is no official method to measure even HCl in ambient air, and we usually go to NIOSH method. We don't measure routinely aldehydes like formaldehyde, acetaldehyde, benzaldehyde, and as with the new administration in United States and with global warming, everybody now talk about greenhouse gases, and our technology, the IR technology, FTIR, is the best for methane and those gases like nitrous oxide, CO, and CFCs. So we understand that industrial area contain a blend of dozens of pollutants, and if we are measuring just one, it doesn't mean that we don't smell the other or we don't breathe them. So the second question is what the source of the emission. And usually if you ask people, they will tell you, yeah, it's coming out of the chimney, coming from the flares. But actually, because we measure them for so long, and because we invest a lot of money of reducing the emission going out of the stack by scrubber, RTOs, CTOs, all kinds of filtration, now the main source for the emission are fugitive emission, and they come from tank farms, product terminal, equipment failures, human error, cooling towers, and evaporation pools. The next question is, where should we measure them? As we know, air pollution moves with the wind. So if we're going to put our point monitor or monitoring station in point I, H, A, G, we will not measure nothing. If we will put our point monitor at point E, we will bias the result high because it's not representing the whole fence line. And that leads to the understanding that if you want to do a good characterization of the emission from your facility, you must measure along lines. Or in other words, open path measurement along fence line dramatically improve the ability to represent the emission when measurements are near the source. What we see on the right is actually from GD52 of the EPA, and it says if you want to reduce your emission and if you want to know your annual emission, the basic for all of that is long-term fence line real-time monitoring. Because we discussed before that equipment failure and human errors are not permanent in time nor in space, a continuous 24/7 spatial monitoring system is required. We don't know when the person will do a mistake or when the pipe will crunch. And it's very easy to understand. If I find the problem, I solve the problem faster, then I reduce my emission. And that understanding went into the regulator, also in Israel, in Canada, in the Arab countries, and also in United States. And in 2015, there was the federal fence line rule that says that every refinery must measure benzene on the fence line. We're going to discuss it maybe in next week presentation. But it also allows you to use an open path instrument for that. And then California took it one step further with two regulation, AB 1647 and AB 617. And a lot of time you need to do root cause analysis and a lot of other rules, like you can see in this slide. Actually, in California, and that will be my next presentation next week, they asked the refineries to measure 20 compounds and report to the public on real-time basis, and also alert when they are exceeding the limit. The rule was implemented in January last year with, I think, 3 months delay. But today, I think every refinery above 40,000 barrels a day need to implement this regulation in California. The Canadian, just in the last month or two, also did a change in regulation, extensive LDAR project, and fence line monitoring, but they took it one step further than the US. They need to measure not just the benzene, but also 1,3-butadiene and all the rest of the BTEX. And it's quite a lot of money doing the LDAR project and the fence line monitoring. As I told you before, the first time I was at 4C was last year, and lucky for me or not lucky for me, it was all over the news that 10 refineries in the United States were exceeding the benzene rule, and actually most of them were in Texas. We are all agreed that it's not good in terms of compliance, but for sure also not for public relations. And then I decided to do exploration about those refineries. And one thing that I found that in Philadelphia refinery, the biggest, I think, refinery in east of United States, they found high concentration of benzene before the explosion. They didn't have the real-time data, but afterwards they analyzed the tubes and they find out concentration in ppm levels of benzene. Imagine what was the concentration of other gases like the total alkane over there. And if someone could alert them in real time and they could solve the problem, maybe this explosion would have been avoided. Again, it's not just the refineries, and now with the COVID, we start the operation, we stop the operation, COVID, weather, all the world become crazy, and that situation can cause leaks. And just a few months ago, there was a leak at LG chemical plant, 11 of styrene, 11 people were killed and 1,000 were injured. And our technology easily can sense styrene and other chemicals. And again, maybe if we could find the leak while it was small, we could eliminate the big leak. We got a lot of inquiries from Texas in the United States about ethylene oxide. And that's because ethylene oxide, for sure, it's very explosive, but also very dangerous compounds. And we did a campaign and we proved that we can measure ethylene oxide in less than 1 ppb on the fence line. And how we can do it, it will be in the next few slides. So that is the background, and now let's talk about the system. So what we see is a monostatic configuration, and actually the monostatic configuration is Robert Kagan, our senior scientist Canadian patent. Everybody use it, but he was the inventor. And what it means monostatic configuration? It means that the source of the light and the detector are in the same place. We shine a beam of infrared light into a retroreflector. That's the golden mirror that you see on your right. The energy bends back. On the way, it reacts with the different molecule in the atmosphere that absorb lights in different region, and that's why we got different spectral signature for different compound. How we do the quantification? We use Bell-Lambert law that says the absorption equal constant multiplied by the concentration and the path length. If we know, and it's easily to know what is the path length, we can measure the absorbance. So now we can tell you what is the concentration based on official US EPA method. But it's not that easy because a lot of compounds absorb light in the same region. And how I know, let's say in the picture on the right, green is what we are measuring in the field, and it's a superposition of methanol, cyclohexane, and triethylamine. And how we know that it's those compounds, and how we know that we don't miss other compounds, and how we know what is the concentration of each one of them, that's the know-how about the D-fenceline system. So first of all, you need to take into account all the interferences, and you have to have an algorithm that can compare shapes, not groups, like some of the manufacturer mistakenly do. The strength of the FTIR is simultaneous multing compounds, but this is also can lead to a lot of false positive and false negative if you don't know how to write the accurate spectral method, and if you don't know how to do good quality assurance, as you're going to see in the next few slides. What we discussed for FTIR, it's also applied for UV DOAS. Here you can see all the BTECs that absorb light in the same region, including the ozone. So spectral validation should be required also when you do a UV DOAS measurement. Because I'm lucky and Robert is part of our staff, I asked him, you were one of the people that actually wrote the method for the EPA. You were the peer review of the method. Why didn't you ask for spectral validation in the method? And he told me that back in the 90s, the computer power wasn't good enough to do it in real time. And what they thought is that you go out to the field, you do a 1 day measurement or 1 week measurement, and then spectroscopists like Robert will sit 1 month to analyze it. And what actually Atmosfir did is took Robert Kagan procedure and tried to automate it. So now with every number that we will report, you can click on the number and it will open spectral validation. What you see in red is reference spectra from NIST of ethylene in this specific sample. And in blue, it's what we are measuring in the field. So now you can be positive that what we report is what there is in the field. And if the shape doesn't look the same, meaning we got problem with the analysis. If you don't have this ability, your instrument is like a number generator. You cannot be sure that those numbers are right. So you must have online spectral validation. As we discussed before, knowing that I've got a problem sometimes is a bigger problem. So we want to tell you where the emissions are coming from. And again, we use an official method called OTM10. And because air pollution goes with the wind, we can find high concentration of the emission on one segment of the fence line. And then if the wind will change direction a little bit, we will find high concentration and different segment of the fence line. Then we will back triangulate the wind and we can tell you the origin. We can easily tell you if it's coming from your facility or from your neighbor facility, but we will not tell you if it's coming from the specific flange. We can give you the area, let's say 50 meter by 50 meter or 100 meter by 100 meter, but this technology will not tell you what is the flange. For that, you will need to take your sniffer team or your LDAR team with OGI cameras or with sniffer and find the leaking problem. We will do the job easily for you, and we will put all the data on Google Maps. So what you see in the circle, the brighter the color, the higher probability that the emission is coming from that area. So now you can send your people, see over there. And this is very important when in the area you've got a neighbor for gas station or neighboring facilities, potential sources. Now fence line become a word that everybody use, and everybody and every technique say that they do fence line. So I put this table to compare different technology from open path instrument, the D-fenceline system that we use in FTIR or UV-DOS, to high-end point monitor that can be fixed or mobile like GC spec or PTRMS, or OGI cameras for total VOC, or even one step further, spectral camera, spectral imaging camera. Or we can go to the low-end point monitor like the passive sorbent tube, or a very cheap point monitor like PIDs or electrochemicals. And in this table, we compare the detection limits, the monitoring coverage, if there is official method or not, if it can work 24/7, if it's a developed technology and product, if we can use it for flux estimation, and also price. And you can see that in almost any category, the open path instrument for fence line uses wins. Maybe for price, the passive sorbent tube wins, but I think for the rest, we are equal or better than the other technologies that we also implement in our company. At least in a few countries or region, what important is that there is official method. And there is an EPA method called TO16 that allows you to use this technology to measure almost any gaseous in the atmosphere. Most of us know TO15, it's a gas canister gas analysis, or method TO17, it's the sorbent tube with thermal desorption gas analysis. And in between, there is the TO16 using FTIR for monitoring gases. If you don't like the US EPA method, you got ASTM method and European method that say the same. About the plume characterization, source location, and flux estimation, there's another US EPA method called OTM10. And with that, we do the source location and the flux measurement. Why use an official technology and method? First of all, we got official QA/QC procedure. The method and technology was validated, and we can pair instrument because there is a definition for the detection limit. So what are the quality assurance in Atmosfir D-fenceline System? First of all, we're monitoring the single beam quality and the signal to noise ratio. Second thing, God gave us something like internal standard that calls nitrous oxide. In the 90s, all over the world, the concentration of nitrous oxide was around 300 ppb. Today, 20 years later, the concentration now is 330, meaning that the global concentration changed by 1 ppb or less every year, meaning 0.3%. So you cannot buy a calibration gas accurate as the nitrous oxide that God gave us. So with every measurement that we measure, we do a quality assurance and we measure the nitrous oxide, and the concentration should be plus minus 10% of the global concentration. In the 90s, it was 300. Today is 330. Second thing that we want to make sure is that our detection limit is less than the threshold or the desirable threshold that we need to measure. Otherwise, our results or our instrumentation is meaningless. And what is the minimum detection limit? Again, we can go to the official method, and then it says usually the detection limit is given as 3 times the standard deviation of the noise of the system. So now we can compare different manufacturer, different solution. And the last thing, we want to do a correlation coefficient. What I call a spectral signature reliability or spectral validation. A few of the problems that I find with other integrator or manufacturer of equipment, that for that they use the R square. But R square is statistical to measure R close data or groups of data compared to the regression line. It's not good comparing shape. For comparing shape, you need a different correlation coefficient, not the statistical R square. And what we're going to see in the next slide is the experiment that we did. We run over 800 data analysis manually. Our scientists look at each one of the spectrum, and they validated 59 ammonia hits, 55 out of the 800, just 59, 55 total alkanes, 2 xylenes, etc. If you would use the R square as your filter for validate data, and even if you take 0.7 as your cut point, then you will have just 35 hits of ammonia instead of 59. If you're going to use the other quality assurance in the method, meaning that your signal is 3 times the error, then you will have 76 instead of 59. In other words, if you're going to use an R square, and I think most of the manufacturer or the equipment provider use, you filter out many validated values, meaning you got a lot of false negative. And if you are relying on the signal to noise ratio, then you bias your result high and you got a lot of false positive. Even a combination of the two will not give you the right result. And to show you how it looks in real time, so on the right, it's analysis based on R square. And the picture on the top, you can see blue again is what we are measuring in the field. Red is reference spectra, NIST reference spectra for ammonia. And you can see that there is for definitely ammonia, but the R square give you a result of 0.11. meaning that if you're going to use R square, all those ammonia heats and toluene heats will be ruled out. We will not report them. That's why we got our own coefficient factor, and our coefficient factor will pass those detections. Again, if you're going to use 3 times the error, and now you can see in red benzene and blue, it's what we are measuring in the field. So now you're going to see that you will have a lot of false positive, meaning the detection is not true. Okay, so now we discussed the need for spectral validation, and now you should do it. And if you don't do it right, you will have a lot of false positive and false negative. But in the last few years, the threshold and the need for a better detection limit grow, especially now in United States. We are talking about, I think the Texas for ethylene oxide is now 2.4 ppb, and benzene, at least in my country, dropped down for almost 3 ppb. So we need to push the instrumentation down. And when we automated our analysis, we wrote a pattern that allows us by spectral averaging reduce the noise of the instrument and reduce the noise of the atmosphere. And what we see in the table here, it's actually ppb. In ppb detection limit before spectral averaging and after spectral averaging. And what you can see that using our algorithm, we can improve any instrumentation by a factor of 5. This was a chemical, and now we can go to petrochemical industry. And again, we can see something like average of factor of 5. Some of the compound we got factor of 10, some of them factor of 3, but for sure we can improve between 3 to 10. We got clients in the semiconductor industry, and in the semiconductor industry, I'm not talking about fence line, I'm talking about a very clean environment, in clean rooms, etc. So the air over there is temperature control, humidity control, and with that we can see much greater improvement, and we can see unprecedented detection limit, like 7 PTT detection limit for ethylene, or half a ppb for total alkane. And here are a few examples again with ethylene oxide detection limit below 1 ppb, and what you see in the picture is just 5 ppb, or benzene 0.9, and you can see just 3 ppb detection limit, or acrolein half a ppb detection limit. So how we verified that what we do is true? So you got 2 or 3 options. One, you can do a bump test with gas cell, or you can inject gas into the path and see what are the concentration. So in this trial we did in South Coast demonstration, and this is what I call the trash calibration. I extended the telescope with trash to be 1 meter, and we injected 102 ppm of benzene to 1 meter open path cell. The retroreflector was 200 meters. And what you can see here is that every time we change the flow rate, we got linear with the benzene concentration. And if we go to see expected concentration to measure concentration, I didn't believe it. And actually I repeated the calculation again before this presentation. And unbelievable, we were in R square of 0.998. So it's working surprisingly good. But not all the time we have calibration gas, or we can release them, and not all the time we got them NIST calibration gas. So what we invented is a simulator. So one of my clients want me to measure a gas, and I didn't see the gas. So how can I make sure that if the gas was there, I could have seen it? So I took the data and I overlay a NIST reference spectra on the spectra that I measure in the field. And then I try to see if I can see it with my analysis. So we did it in two cases, one around 250 meter open path measurement in Houston, humid, and in Israel, desert. We had more than 200 measurement in different concentration and 10 cycle for each concentration. So on the two picture on the top, you can see how the spectra look before we overlay the benzene, and you can see that we can definitely see the benzene, and what you see, it's 2 ppb of benzene with quantification limit of 0.4 ppb. But the other things we want to see, this is how we decide what is the metal detection limit. We want to see in actual life how many of those we can measure in real time. So we did a simulation. So we had a 15% error with the results. And then we want to see how many of the events we can measure. So in Houston, we injected 2 ppb, 3 ppb, and 4 ppb, 10 events each time. So for 2 and 3 ppb, we could identify 80% of the events. Above 4 ppb, we could identify 100% of the events. And we did the same experiment in Israel. And again, 2 ppb, 8 out of 10. But when we went to 4, we could detect all of the benzene events. So for conclusion, fenceline measurement can be the nose for advanced warning if something goes wrong. Human error, equipment failure, we can detect it on real time, you can go and fix it. Real-time data, 24/7 wide area should be implemented if you want to improve the safety. One instrument that we talk about, FTIR, can measure a long list of contaminant. We got clients that measure 6 compounds, and we got clients that measure, as you saw before in the semiconductor industry, 60 compounds simultaneously. We got the ability for unprecedented detection limit below any regulatory threshold, and that can be achieved using Atmosfir algorithm, but we also need a good instrumentation. So if you got good instrumentation, it could be broker or other manufacturer that got stable instrument, then we can drive the detection limit very low. Those instruments are not analyzer. You have to do a lot of quality assurance and especially spectral validation. Now imagine, like in California, you report to the public, and we're going to see in next week presentation what people report to the public. And believe me, you don't want to be in this situation that report high concentration that never been there. So spectral validation must be required. If not, a lot of false positive and false negative can be reported to the public. There is ability to do source location, at least to give you wide area where the emission is coming from. You must have a very friendly user interface that people will use the system. Otherwise, it will be like what we call white elephant that no one use. And you don't need to invent the wheel. So I know that there's a lot of good technology over there, but keep in mind, the US EPA method was written in 99. Today we are in 2021 and we start implementing it. Yeah, we talk about satellite, we talk about a lot of OGI cameras, PTRMS, category ring down instrumentation, but they are not official method. You can go to official method and implement it as a fugitive emission control. Monitoring, meaning supervision and education of your employees, and that for sure what we saw in all our installation improves safety. I will not share with you this data, but in a lot of our installation, we find safety issues, and then the motivation change from environment. Yes, I want this system that I will not have an explosion or a big leak. And I think this solution is a win-win for all involved parties. From the regulator, we will have an easy way to see the emission. For the public, that he can sleep quietly, that if something goes wrong, someone will alert him. And also for the industry. And the industry will have saving costs, saving cost in OPAC, saving more than 50%, reduction of product loss, reduction of fines and permit cost, significant safety improvement, risk reduction, less probability for major leaks, less manpower on site. You don't need less elder people that will go in your facility. You will have emission reduction by shortening the time of leak detection and repair. You will stay in compliance. You will find a problem before the regulator or before the satellite or before the passive sorbent tube, and you will gain a positive public relations. So that's about today. And I think next week I'm scheduled to give a presentation about the implementation of 1180 South Coast rule. And I think it will be very interesting to see how those systems were implemented in California, what was good about it, and what we need to improve. So you got my detail if you got further questions. Thank you.
Thank you so very much, Gilad. Are there any questions? How big an area, this is a question about the satellites. How big an area do satellites monitor at any given time? That depends upon the satellite and the weather conditions, but that's not necessarily for this conference, for this webinar. Okay.
Okay.
Okay, so Gilad, thank you very, very much. Fantastic presentation. And again, want to invite folks next week, the fence line monitoring as it was applied in California will be the discussion, topic of discussion, and Gilad will lead that. Here's a question. Is adding a reference spectrum to the measured spectrum a part of the EPA method QA?
Yeah, you need to do the analysis, but you don't need to do NIST reference spectra. But if you use the NIST reference spectra, then you don't need to calibrate your instrument. So there is a big advantage of doing this quality assurance. Meaning, and it says in the method, if you use a NIST reference spectra and you use the same resolution or better, then you don't need to calibrate your instrumentation. That's meaning that with every measurement that we take, we actually calibrate our system against NIST. So that's what the method says about it.
Excellent. Okay, thank you very much, Gilad. And we are at the limit here. 11:56. So thank you very much, and that
Thank
will
you.
end today's webinar.
Thank you.